In this presentation, I'm going to talk about the effect that the thermal environment has on work performance. I'm going to report about the study where we went to the existing literature that is out there, and we extract data through a meta-analysis, and we try to build a model to predict the effect of the thermal environment on work performance. And we were not able to find a relationship between the two. I'm Stefano Schiavone, an associate professor here at Cal, and this work was led by a postdoc in Singapore, Jose. We've been studying the productivity, the effect of the thermal environment on productivity for 50 years. And why do we do that? Because we have the assumption that we could create for people a specific thermal environment that allow them to work at their best conditions. So suppose that you're in a room, the temperature is set at 72, and you come to the CB meeting. You learn here that we can increase the temperature point, people will be equally happy, and you can save some energy, you can save some greenhouse gas emission, and you can save some money. And then you go to your boss and you say, let's try to increase the temperature point. First or later, you will end up meeting this graph that is here on the left. This one is the relationship that was built by a colleague at the Lawrence Berkeley National Lab around 15 years ago, where they did exactly what we are going to present today. They did a meta-analysis of existing literature, and they found that the peak performance happened at 72 degrees. This is by far the most cited and most used relationship between the temperature and work performance. Something similar, basically the same equation, just with a slightly different x-axis, is present in the Handbook of Fundamentals of ASHRAE, where the peak performance happens when people feel neutral, when you do not feel hot and cold. And for basically every degree in change from your peak performance, there is a reduction of 0.5%. So if you try to increase the temperature point from 72 to 77 Fahrenheit, you will have a drop in performance, something around 2.5% if you use this equation. And then depending on how much is your hourly cost, this is something around $5,000 per employee. And that's most probably is much higher than the energy saving that you may have. And therefore, this is discouraging our ability to increase temperature set points. The researcher that developed this existing model said that it was not very accurate, but they did not specify how low was this accuracy. And so we decided to look for the data and try to see how accurate this model is. Moreover, 15 years has passed since that study, and we look at the literature and we found many more studies out there. And we say, let's try to build a new model. And we use exactly the same approach that they used. Before going to show you the result, I want to give you some information related to work performance and potential relationship with the thermal environment. The first one, something that many people wonder is, can we measure work performance? The simple answer is yes, it's possible, and it's done regularly in many other fields. Worker performance basically is those things that workers do that are relevant for the organization. Often we use the term productivity, but that's not the right term, because productivity is the ratio of input over output, and many times these are not under the control of the worker. For example, if you want to assess the productivity of some of your employees and you are in a design consultancy firm and you calculate how many projects do you bring in, or how many budget do someone bring in. Those do not depend only on the worker, it also depends on the outside condition. How is the marketing is doing? So it's not a fair assessment of the situation. We have nowadays a good understanding of how to measure work performance, and it's done in many ways. First of all, it needs to be contextual. How we measure work performance in one condition is very different for another one. How we assess the performance of a driver for Amazon is very different from the way that we assess the performance of someone that is selling coffee at Starbucks or is designing buildings. There are different types of tests, and in our field, we mainly use cognitive tests or neurophysiological tests. Basically, we try to assess the fundamental bricks that describe our ability to get our job done. Like, for example, how long we can focus. Can we, at the same time, listen to information, process them, and react over them? We can simulate work, like, for example, when you try to hire someone, or we can use ratings. For example, asking someone else, a colleague, to assess your own performance. Another important aspect to take into account is that when we look at this relationship between the thermal environment and performance, we may have a model in our mind. And here there are two of the most famous ones. The first one is named the inverted U, basically because it looks like an inverted U. It was developed more than 100 years ago. And the idea is that there is only one point at which performance peaks. If you're outside that point, then performance is reduced in one side or the other. For example, the stress could be an incentive. How much cash bonus do I give you to increase your performance? We know that if I give you a little bit more, then performance increase. At a certain point, they reach a peak. But if I give you too much, then I incentivize you to cheat, and then performance go down. Similarly, for the thermal environment, or acoustical environment, or light environment. Another model that is sometimes named the inverted extended U model, or the maximum adaptability model, assume that there is a range for which there is not a change in performance. And only when, for example, in this case, it's too hot and too cold, then we see a reduction of performance. Another aspect to take into account is that the model that I showed you before is focusing on temperature. And we know that temperature is only a proxy for thermal comfort. There are other variables that play a role. How much we are dressed, how much clothing we have, the airspeed in the environment affect the result. So we already know that this is a simplified approach to the problem. This slide is a little bit complex, but it's useful for people that want to go deeper on this issue. Why? Because in the slide that is shown here is shown on the vertical axis, the percentage change in performance for every increment of the temperature of 1 degree. All the dots that you see over there are result from human subject experiment that we collect from other researchers. And this equation is useful, this graph is useful because all the performance analysis are done on this type of chart. But then, after that you've done that performance, that assessment, you do not use this chart anymore. So for example, in the case of the model developed by Sepinen, Fisk, and Ley, 15 years ago, they look at this data, they say this one looks like a quadratic model, they fit it, and when the line meets the 0 value, then is where you have your peak performance. When you have this equation, you do an integral and you obtain the equation that we see over here. So coming back to our original objective, how low is the prediction accuracy of the existing model present in the ASHRAE Handbook of Fundamentals? We collect the data, we use the same data that they have, and we run different type of statistics. And the R-square, that is a metric to assess how well your model fit the data, give you an idea of how much of the variability that is present in the data can be explained by that variable, was around 5%. Very, very little. And even more useful information, like the one that you see there on the bottom, the mean absolute error, that give you how dispersed are the prediction, tell you that basically this is a cloud of data. The data are so spread, almost random, that if we fit a model that say there is no relationship between temperature and work performance, we found a similar accuracy. Therefore, the model is not acceptable. When we saw this result, we started to look for the literature This model that's shown over here, it was based on around 26 studies and 150 points. And so we went out there and we found many more studies, around 35 studies, around 360 points. And when we collect this data all together, we started to not fit one model as they did before, but many of them, dozens of them. We use their own equation, we use linear regression, exponential regression, we use several machine learning tools, and we also tested this extended U model, the MAIM. And the result is basically we could fit whatever we wanted. And that's kind of sad, because basically all of these models are correct. Yes, they describe the data, but given that all of them have a very low accuracy, all of them are equally valid. Here's, for example, we show some of them. In one case, the peak performance are around 58 degrees Fahrenheit. In another case, the peak performance is around 72 Fahrenheit. In another case, performance peak in a wider range. And none of these models were significantly better than the one that assumed there is not a relationship. When we found this result, we were very worried. This is going against something that has been around in our industry for a long time. We contact the original author. We try to show what we did. They say that this seems reasonable. Actually, that's a nice way to look at the problem. And so we decide to make the database open so other people can go there and check our result. And we also build an interface. So you can go online and select data from different parts of the world, different type of cognitive tests. Some of them focus on accuracy, others that focus on speed. And what you will see is that basically if you want to prove that performance peak at 75 degrees, you can find that. If you want to find that performance peak at 70, you can find that. If you want to find that performance peak at 80, you can find that. This study has several limitations. These limitations are true for this study and exactly true also for the previous studies. We know that temperature does not describe the thermal environment. It's just a proxy. The way that the data are normalized is problematic, in particular when people tested the extreme condition, like for example, you are at 75 and then I put you at 95. The study used very different method. They used different cognitive tests. And then when you merge together, you lose some of the information. The data of the previous study were not public, so we have to extract those information from graphs that sometimes were developed in 1960s. And we know that there are very large differences among people. So what are we going to do next? The first thing is that we will try to work with ASHRAE to remove that graph from the Handbook of Fundamental, because we think that that graph is hampering our ability to have wider range into building. And there is not enough evidence to support that we need to keep people at 72 Fahrenheit. We have already completed the study looking at the relationship between thermal sensation and performance. It's not public yet, but the results are exactly the same. And something that we care quite a lot is that we want to develop a protocol on how this experiment should be run, how the data should be made public, with the hope that if we have better data, maybe we can build a model. So based on this work, we concluded that work performance does not peak at 72 degrees Fahrenheit and also not at neutral condition. And therefore, we should not use a relationship relating work performance to the thermal environment. We were not able to find a relationship in the typical range that we see in building, that is something between 68 and 86 Fahrenheit. And even when we look at for wider range, the situation was similar. Our results are not proving that the thermal environment does not affect performance, for all the limitations that I mentioned before. Our results are telling us that we do not have right now an equation that we can use that we could implement in software to make a relationship between work performance and the thermal environment. Thank you.